So in the previous video, we were looking at compounding interest, and we used our simple interest formula and ran through a bunch of computations in order to calculate compound interest annually, and then we did it semi-annually, or every 6 months. Well, we have a formula that will shorten that work, and this is called the compound interest formula. So the compound interest formula says A equals P times the quantity 1 plus R divided by M in the quantity, and that 1 plus R divided by M gets raised to the N power. So A is the future value, P is the principal, so the amount invested or borrowed, R is the annual interest rate written as a decimal, M is the number of times interest is being compounded per year, and N is the number of time periods, or the number of times we compound. So, if interest is compounded annually, then M is equal to 1. If it's compounded semi-annually, then M equals 2. If quarterly, then M equals 4. If monthly, then M equals 12. If daily, then M equals 365. So basically this M is how many times we're computing interest per year. And so again, if it's annually, that's once per year. If it's semi-annually, that's twice per year. If quarterly, that's 4 times a year, and so on. Also, N is going to equal M times T. So if we're investing for 3 years and we're compounding semi-annually, then we're going to take 2 times 3, and that's going to be 6. So our value of N would be 6. So again, M is the number of times interest is being compounded per year, and so T is the number of years, and so if we multiply those two, that gives us the exponent here, N. Now, just as a quick review here, and to show you the use of this particular formula, I want to pull back in examples 5 and 6 from the previous video and show you that we could have done these problems much more quickly by using our compound interest formula. And I'm going to write our compound interest formula down right here. It is equal to, or A is equal to P times 1 plus R over M raised to the nth power. So again, I just want to show you we could have come up with this answer much more quickly with this formula instead of having to go through step by step by step. So in this problem, we were investing $5,000 for 3 years compounded annually at 4% interest. So our amount that we would end up with after the 3 years is equal to the principal, which would be $5,000, times 1 plus our interest rate, which is 0.04 if we write that in decimal form, divided by M. M, in this case, we were compounding annually, so we're doing it once per year, so M equals 1. And so we were doing that for 3 years, so N is equal to, again, M times T, so that would be 1 times 3, which would be 3. So we would be raising to the 3rd power. Now, 0.04 divided by 1 is 0.04. So this would be 5,000 times 1 plus 0.04 raised to the 3rd power. And 1 plus 0.04 is 1.04. So we have 5,000 times 1.04 raised to the 3rd power. So if I bring in my calculator, 1.04 raised to the 3rd power is 1.124864. So we have 5,000 times 1.124864. And if I take 5,000 times 1.124864, that is $5,624.32. $5,624.32, which is what we computed right here. So we could skip steps A and B and jump right to the answer in C. This would be the value after 3 years by using our compound interest formula. Now we could do the same thing in example 6. So in this case, we were going to compound the interest every 6 months, which means semi-annually. So for this problem, again, we started with $5,000. So our principal is equal to $5,000. Our rate is 4% or 0.04. Our time is 3 years. M in this case is 2 because we're doing it semi-annually. We're calculating interest twice per year. And then the number of times that we calculate is going to equal M times T, so that is going to equal 2 times 3, which is 6. We had to go through this process 6 times. That's what N is. It's the number of times we're going through the process. So again, if I used my formula, A equals P times 1 plus R over M raised to the N power, then in this case, this would be 5,000 times 1 plus 0.04 divided by 2, because M is 2, raised to the 6th power. So 0.04 divided by 2 would be 0.02. So we have 1 plus 0.02 raised to the 6th power, and 1 plus 0.02 is 1.02. So we have 5,000 times 1 plus, or we have 5,000 times 1.02 raised to the 6th power. And if I bring in my calculator, 1.02 raised to the 6th power is 1.126162419. So this is 5,000 times 1.126162419. And so if I take 5,000 times the 1.126162419, that is $5,630.81 if I round to the nearest penny. So $5,630.81, which is the same answer we obtained after going through this process. So again, our compound interest formula, the beauty of it is it's going to let us jump to the amount, the future value after the time period of t years. So now let's take a look at example 7. Carl puts $8,500 into a savings account that pays 2.4% annual interest compounded monthly. How much money will Carl have in 5 years? So again, this is a compound interest formula. We're compounding monthly, which means 12 times per year. So for this problem, Carl's investing $8,500. So that is P, that's the principal. The interest rate is 2.4%, or in decimal form, 0.024. We're compounding monthly, so M is equal to 12. We're leaving it in for 5 years, so time equals 5 years. And so that means the number of times that we're going to do the computation will be M times T, so that's going to be 12 times 5, which is going to be 60. So N's going to be 60. That's the number of computations we would have to go through. That would definitely be no fun to do the same way that we did examples 5 and 6 in the previous video. We wouldn't want to do that, so this formula is going to come in handy. So again, our formula is our future value is going to equal the present value, or the principal P, times 1 plus R over M raised to the N power. So that is $8,500 times 1 plus 0.024 divided by 12 raised to the 60th power, again 60 because 12 times 5 gave us the 60 there. So if we follow the order of operations, let's do this on the calculator. If I take 0.024 divided by 12, that is 0.002. So I have 1 plus 0.002 to the 60th. and 1 plus 0.002 is 1.002 raised to the 60th power. Now if I take 1.002 and raise that to the 60th power, that is 1.12736174. So I have $8,500 times 1.12736,174. And so if I take $8,500 times 1.12736,174, that is $9,582.57 if I round to the nearest cent. So after 5 years, Carl will have $9,582.57. So how much money will Carl have after 5 years? $9,582.57. Now I do want to show you though, I did this by following the order of operations. I've done that on all of the examples so far, but the truth is I could have entered this like this in the calculator if you have an appropriate calculator for this. So let me show you. If I enter this problem, 8,500 parenthesis 1 plus 0.024 divided by 12, close the parenthesis, and then raise that to the 60th power, that gives me the $9,582.57 that we obtained here. So I could punch this in directly instead of having to do this one step at a time. And that will be the easiest. You just have to be careful to make sure you use your calculator correctly for that. Let's do one more example on this video, and then we'll move to, I believe, what will be our last video. So example 8. On the birth date of their grandchild, the grandparents want to start a college fund that will grow to be $50,000 when the grandchild turns 18 years old. If the annual interest rate of the college fund is 3.2% compounded quarterly, how much must the grandparents invest now in the fund? This is kind of like the present value problem that we did in the previous video. What we have here is we have grandparents wanting to invest a certain amount now, the present value, the principal, and they want that to be worth $50,000 in 18 years. So the question is, how much do they have to invest now in order for that to happen? So we can again do this with our compound interest formula. A equals P times 1 plus R over M raised to the n power. The difference is what we have at the moment is the future value. So we have that A equals $50,000. And again, in this case, the question is, what do the parents have to invest now so that this will be worth $50,000 in 18 years, okay, when the grandchild's ready to go to college? So we're looking for P. What's P got to be? Now we know our interest rate. Our interest rate is 3.2%. or 0.032. We know that we are going to be compounding quarterly, so M is going to be 4. Quarterly means 4 times per year. We're going to have the money invested for 18 years, and so that means N, the number of calculations, is going to be 4 times 18. 4 times 18 is 72. So we'd have 72 different computations that we would have to do if we did it like we did examples 5 and 6, which of course we don't want to do. So using my formula, we have $50,000 is going to equal the principal, whatever that is, times 1 plus R, which is 0.032, divided by 4, raised to the 72nd power. So the 1 plus 0.032 divided by 4 raised to the 72nd power, that's just a number. So I want to figure out what that is. So 50,000 is equal to P times. Now if I take on my calculator 0.032 divided by 4, that is 0.008. So I have 1 plus 0.008 raised to the 72nd power. And 1 plus 0.008 is 1.008. So I have $50,000 equals P times 1.008 raised to the 72nd power. So if I take 1.008 and raise it to the 72nd power, that is 1.774836,338. So 50,000 is equal to P times 1.774836,338. So if I divide both sides by that 1.774836,338, that's going to give me what P should be. So P is going to equal 50,000 divided by that 1.7748, blah, blah, blah. So 50,000 divided by 1.774836,338, that is equal to $28,171.61 if I round to the nearest penny. So again, $28,171.61. So if the grandparents invest $28,171.61 on the day that the child's born, and if they're getting 3.2% compounded quarterly and they leave it there for 18 years, then that $28,171.61 will grow to be $50,000. So we're going to stop this video and move on to the next video.